For today's notes, you will need IC 77. This is the first part of Standard 18, where we're going to talk about segments and how they interact with circles. For this standard, there are some algebra applications that you'll need to know, and they do show up on the assessment. So we want to make sure that we do a little bit of algebra review at the beginning. We are going to need to know how to simplify expressions that are binomials that have been squared. So if you go back to what you know about squaring, that means that we need to be able to multiply whatever the expression or number is by itself. And so we can't take that exponent and distribute it across the addition sign. What we need to do is really think about what the definition of squaring is, which is multiplication by self. That means that we actually have double distributing to do, or some of you might have learned this called FOIL back in your Algebra 1 days. So we need the x to distribute to both the x and the positive 8. X times x is x squared, and x times positive 8 is 8x. And then that positive 8 does the same thing and distributes to both the x and the positive 8 to give us another positive 8x and a positive 64. To finish the simplifying process, we're going to combine the like terms. X squared does not have an exponent shared with any other term, so it's on its own. Positive 8x plus 8 more x is positive 16x, and then positive 64 is our constant term. So our final official simplified expression for x plus 8, the quantity squared, is x squared plus 16x plus 64. Just another example of that where there's a coefficient on the x. So if we want to do the quantity 3x minus 5 squared, we need to multiply 3x minus 5 by itself. Distributing 3x to 3x gives us 9x squared. Distributing 3x to negative 5 gives us negative 15x. Negative 5 times 3x is another negative 15x. And negative 5 times negative 5 is positive 25. Again, we have some like terms in the middle of that expression. So 9x squared minus 30x plus 25 will be our final answer once we combine those like terms. So we'll watch out for other situations where we get to use that algebra skill of squaring a binomial. One more piece of review. We've talked about tangents to circles before, but remember that those are lines or segments or rays that intersect a circle at exactly one point. So today's focus is things that are true about those tangents that intersect a circle at exactly one point. Our first theorem looks at the relationship between a tangent to the circle and radii that are in the circle. So if we draw in a radius from the center point to the point of tangency, the place where that tangent intersects the circle, it is always going to be perpendicular at that intersection, that upside down T symbol. So the tangent is always perpendicular to any radius or radii that's drawn to that point of tangency. That means that we can mark this angle as a right angle. And then often what you'll see is there'll be another connector, usually from the center out to a point on the tangent. And so now we have a right triangle and we have opportunities to use lots of our previous standards, like Pythagorean theorem, c squared equals a squared plus b squared, or maybe special right triangles if we see a 60 or a 30-degree angle or a 45-degree angle, or even maybe some sine, cosine, tangent stuff if we see an angle of some other size. The second theorem that we'll learn about tangents are when tangents are coming to a circle from a common external point. So this point would be that common external point. This is a tangent that intersects the circle at that location, and then the other tangent intersects at that point of tangency. When that's the case, those tangent segments are always going to be congruent to one another. So the distance here, let's call this segment BC. Segment BC is going to be congruent to segment AC. So those tangent segments are going to have the same measure. That happens because if we think about connecting those tangents to a radius at that point of tangency, we just learned in theorem number 1 that there are right angles at each of those locations. These radii are congruent because radii are always congruent. And then if we connect that center point to the external point that they have in common, we have a reflexive property opportunity here with that new segment. These triangles become congruent by hypotenuse leg theorem back from first semester, and then these tangent segments are congruent by CP/CTC. Corresponding parts of congruent triangles are congruent. Now you don't need to know that whole proof of why that happens, but that's the justification for why these tangent segments from a common external point are always going to be congruent. All right, that's the learning for today. So now it's just all about doing examples and finding ways to apply those ideas to solve problems. So if we look at this first problem here, we do have a tangent right here to the circle. That line intersects the circle just at B for the point of tangency. And we do have a segment that's coming out from the center. So this is a radius that would make a right angle with that tangent. We also have a 45-degree angle given. So if this angle is 90 and that angle is 45, that means the remaining angle in the triangle would also be 45. So this is going to give us an opportunity to use our special right triangle theorems. When we're working with our 45, 45, 90s, remember we have two legs that match across from the 45. So that means the whole diameter of this circle is 10. Looking for CB then, that would just be the radius. So we could divide that 10 by 2, and CB will turn out to be 5 centimeters. Looking ahead at the next example, our goal is to find AB, which is this tangent out here. Again, we've got a tangent and a radius that are intersecting, so they're going to make a right angle. If I'm looking for AB, I'm going to go ahead and put an X on that side just to remind myself that that's the goal. But then I'm thinking without the presence of an angle, I'm going to need to use Pythagorean theorem, which requires me to know 2 of the 3 sides. This side over here, using a little segment addition postulate, is going to be 13 centimeters. And then if we think a little bit creatively about CB, that's a radius. So is this right here. So I can take that 5 centimeter label and move it to segment CB, which means now I have the hypotenuse, the C part of my Pythagorean theorem, and then I have the A and the B as well. We go ahead and square everything and then subtract 25 from both sides. We're going to end up with 144 equal to x squared. 144 is a perfect square, so officially the answer would be plus or minus 12. But since our x represents a segment length, it's just going to be positive 12, which means AB is equal to 12 centimeters. All right, moving to example C. One more time, we've got a tangent and a radius, so I'm going to go ahead and put that right angle on the picture where it belongs. The goal is to find CB, so again, I'm going to put an X on that side. And I'm noticing I've got a 55-degree angle to use as a reference angle. So if I'm thinking about sine, cosine, tangent, I've got the opposite side and the adjacent side as being important, which means a little tangent equation, tangent 55 equals opposite over adjacent. Remember to solve when the variable's in the denominator, we want to multiply both sides by that variable. And then to isolate that x afterwards, we're going to need to take tangent 55 and divide both sides by that expression, which will leave us with a division problem to go to our calculator with. Knock some calculators off the shelf back there. 9 divided by tangent of 55 is 6.30. We're going to need to round this one because we can't leave that answer exact. So we're going to go 2 decimal places like we normally do. 6.30 centimeters for x, which was actually CB as well. All right. Example 2 at the bottom. One more time, we've got a tangent to a circle and we have a radius They're asking us to find the radius of the circle, so I'm going to go ahead and put an X there since I don't have it. No angles given to us, so we can't use our special right triangles or our sine, cosine, or tangent, which means Pythagorean theorem is going to be the goal. However, we're missing part of this side. We're going to need to know what that whole segment from C to A is in order to use it for the hypotenuse in our Pythagorean theorem. Since I marked this radius with an X, I could mark this radius with the same X, and then segment addition postulate would tell me that the whole segment would be X plus 9. This is where that algebra review that we started with earlier today is going to come in handy, because that hypotenuse, that C, is a binomial that needs to be squared, and then our A and our B would be X squared and 15 squared. Remember, when we square a binomial, we really need to think about multiplying it by itself. So we write that out twice to make sure that our brain can do all of that distributing we reviewed earlier correctly. So distributing the x to both gives us x squared plus 9x. Distributing the positive 9 to both gives us another positive 9x and a positive 81. And then the other side is x squared plus 225. Now, before we get too worried, if we try to get these x squareds onto the same side of the equation, they are actually going to end up making 0. X squared minus x squared is 0 on both sides of the equation. So we really are just left with 18x plus 81 equal to 225. So even though the simplifying part of this was a little bit complicated, we just have a regular equation to solve where we need to subtract 81 from both sides. And then after we do that, we're going to end up dividing both sides by 18. So 18x equals 144. Divide both sides by 18. And x, which is equal to the radius, which is what they asked me to find, is going to be equal to 8 centimeters. All right, go ahead and flip the page over to the second part of the examples. We have a few more examples to go. This problem looks a little bit different to me because we don't have the radii drawn in to meet the tangents, and we actually have two tangents in this picture. So if we think back to our second theorem, remember, when tangents come from a common external point, they will be congruent to one another. So my equation this time around will set 5x minus 3 equal to 77. We'll go ahead and add 3 to both sides. So 5x is equal to 80, and then divide both sides by 5 to solve for x. X will be equal to 16. Looking at example B, we don't know a whole lot about the part of the picture that has the x on it, but they do have a radius dashed in here connected to this tangent, so I'm going to put a right angle there. If that's 90 degrees and that's 45 degrees, I think I'm going to be able to use that 45-45-90 relationship one more time. The two legs of that triangle should match, which means I can move that 12 centimeters out here to AD. And then because AD is a tangent from the same external point as this tangent, these are going to be congruent to each other, which means x is just equal to 12 centimeters. Final problem here. This is an example where we actually have quite a few tangents that are from a common external point. So when we're looking at this diagram, we'll come back to this perimeter clue in just a minute because perimeter is the entire distance around the triangle, which I don't think I'm quite ready for yet. If we know that AC is 15, first things first, I want to make sure that we don't make a mistake. These two tangents are not from a common external point. This tangent starts at point A and this tangent starts at point C. So we cannot mark that these are congruent, which means we can't divide that 15 by 2. If we look at the next segment from A to F is 8.5. That number represents a tangent from external point A So I would be able to mark that that is congruent to this tangent from the external point at A as well. If this is 8.5 centimeters and the whole thing is 15, some quick subtraction, so 15 minus 8.5 would help me to fill in this tangent segment between C and B. And then thinking about this C as being an external point, we have two tangents from that common external point, which would be congruent as well. So that 6.5 can be copied over to segment CD. Now I am not given any information that will help me to track down DE or FE directly, but it would be possible for me to mark those as being congruent since they're from a common external point. Since they're both missing, I'm going to call them both X. And then I'm going to circle back around to this perimeter clue. If the perimeter of the entire triangle is 40, I've got one full side that's 15. This side would be 6.5 plus X. And the third side would be X plus 8.5. Perimeter adds all of the sides together. So once I have all three of those sides added together, I know the total has to be 40 if that's the value I was given for my perimeter. So if I combine together my like terms, I'm adding 15, 6.5, and 8.5 together. That's going to be 30. Adding those x's together will give me 2 x's. If we subtract 30 from both sides, we're going to end up with 2x equal to 10. And then dividing by 2 lands us with x equal to 5. Do a quick check. The goal was to track down the length of segment FE, so that's the value I just found, and the units for this entire problem are centimeters. So 5 centimeters. We'll finish out today's notes dealing with tangents and the 2 theorems that we can use related to those types of segments, rays, or lines. Thanks for watching. We'll see you back in class.